Hi, Year 12. I'm going to take you through question 1 on the Unit 6 end of topic test. I did already start a video on this actually, which you may be able to see from the fact that there's some scribblings on here, and then it just stopped, probably storage problems again. So I'll just quickly talk you through some of the annotations that I'd already made. So this is question 1, which is the retrieval practice question on this end of unit test, and it's pertaining to unit 4. Looking at some organic chemistry of alcohols and halogenoalkanes and different mechanisms, namely nucleophilic substitution. So you've got a reaction sequence here, and it says halogenoalkanes are useful compounds in synthesis. A reaction pathway is shown. So before I actually get on to the question, whilst it's not necessary, I am just going to kind of go through and annotate and label with what's happening, just so I can get an idea of what this question is about. So I've got reaction 1, where I'm starting here with a halogenoalkane, which has also got a hydroxy group there, and we've replaced that halogen or halide ion with an OH group. So that's going to be nucleophilic substitution, with sodium hydroxide there providing an OH minus nucleophile. That's the reagent, that's the nucleophile. The conditions are going to be aqueous, because that will give rise to the nucleophile, as opposed to the OH minus ions acting as a base during base elimination. So that gives us our diol. Okay, we've got 2 OH groups. Then in reaction 2, we're not given the structural formula, we're given the molecular formula, C4H6O2. And we can see here, if we check our atoms, C4, we've got 1, 2, 3, 4. We've still got 4 carbons, nothing's happened there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've gone from 10 hydrogens to 6 hydrogens, which means we've lost 4 hydrogens during this reaction. And oxygen, 1 there, so 2 and 2 there. So we've not gained or lost any oxygen, which means that this reaction here must have been an oxidation reaction, classified by the loss of hydrogen here. And our job in a minute, the next question, is to work out what this product is. Now, if we oxidise an alcohol, we're going to get either an aldehyde, a ketone, or a carboxylic acid, and we need to work out which one we've got. So if we've got here these OH groups attached to carbons, which are attached to 2 other hydrogens, and then an R group, one R group, that means that we've got primary alcohols. Both of those are a primary alcohol. You oxidise a primary alcohol, you're going to get an aldehyde, or you're going to get a carboxylic acid. We are not going to get a ketone, so we can rule that out. The number of hydrogens we've got, or rather, sorry, the number of oxygens we've got, that means that we know we're not going to have a carboxylic acid, because we've got the same number of oxygens. If we went to a carboxylic acid, then obviously we'd have this functional group, we'd have gained an oxygen, so we can rule that out, which means this must be an aldehyde, and if we've got 2 OH groups, it must be a dial. We must have 2 of those aldehyde functional groups. Okay, reaction 3 gives us compound Z. We don't know what that is yet. So question 1, give the IUPAC name for this compound. So you need to know your priority table here. You need to know that an OH group will take priority over a halogen, which in turn will take priority over an alkyl group. So that means this is going to be carbon 1, and that's going to be carbon 2, and that's going to be carbon 3. So the stem of our chain is prop, because we've got 3 carbons in it. We've got a methyl group attached to carbon 2. Our suffix is going to be ol, because this is our priority group, and our prefix is going to be bromo. So this is going to be 3-bromo, and then you could say 2-methyl, but actually where you've got 3 carbons in your chain, it can't be anywhere. You can't have a methyl group on carbon 1 or 3, because that would make it a straight chain. You'd lose your branching. So it's unnecessary to say 2-methyl. So 3-bromo methyl prop an, I have to come down here because I've drawn stuff there, propan 1-ol. Wherever you have a carbon chain of 3 carbons or more, you need to put the numbers in because isomers could exist. Okay, question 2. Reaction 1 occurs via nucleophilic substitution mechanism. We've already established that. Explain why the halogenoalkane is attacked by the nucleophile in this reaction. So, explain why the halogenoalkane is attacked by the nucleophile. I'm actually going to switch to blue. Right, there are 3 marks here, and this is the kind of question where, you know, it's going to be kind of a sentence a mark. So, what happens in nucleophilic substitution reaction? Well, you've got either negative, something with a negative or a partial negative charge. Because a nucleophile is not defined by the presence of a negative charge, it might be a partially negative charge, and you don't want to be talking about this. The important thing here, before I even look at the mark scheme, I know there's going to be something on here about the lone pair. So you're going to have to say something about, I'm just going to jot down a couple of ideas. The lone pair on the oxygen, and we're going to need to say something about the partial charges here on the CBr bond, and that's 2 marks. So the 3rd mark is probably going to come from saying something about how these partial charges arise. So electronegativity. I'm going to put here difference, because this is going to be, you're going to need to make a comparative point here. If you just say bromine is electronegative, that does not make it clear that carbon is less electronegative than it. It needs to be a comparative point. So I am going to say that bromine is more, okay, we want a word, more, less, you know, greater, whatever, is more electronegative than carbon, thus has a partial negative charge, leaving carbon with a partial positive charge. Then I'm going to say the lone pair on the oxygen is attracted to this partial positive charge. That's it really. I guess I've got kind of 2 sentences, but I think that, oh blimey, that covers all 3 points. I've said that there are partial charges, I've said how they arise, and I've said therefore that the lone pair is attracted to that. Okay, next question says the infrared spectrum of compound Y shows significant absorption in the range 1680 to 1750. Draw the displayed formula. I'm going to highlight that, and I'm going to write here all bonds. So I'm just, to make this easier, so C4H6O2, C4H6O2. Okay, so that's what we're dealing with. So I'm going to need my data sheet. We've already worked out that this is an aldehyde, a di-al. But I'm just going to double check based on the information that I'm given. So it's the, what was it, IR, so we want table A, if I just do that a bit, table A, and to be honest, you will come to just know this, but if you don't, then you can find the carbonyl group there, 1680 to 1750. So that tells us that we have got that functional group, and we know it's a dialdehyde, so we're going to have 2 of those. So C4H6O2, remember the alcohol had, what was it, CH2OH, CH3, bums, CH2OH, didn't quite give myself enough space there, but on carbon 2 we had a methyl group. So we're going to have 1, 2, 3, 4, we need our 2 aldehyde groups. We need a hydrogen there. This is the displayed formula, and I imagine a common mistake here was to just bung in a CH3 group, which would lose you the mark, which is such a shame, because if you've gone to the difficulty of working out what you've produced and you lose marks there because you've just forgotten to show those bonds, that's, yeah, a kick in the teeth. So that's going to be the displayed formula of compound Y. And that's it for question 1. Yeah, I will do more for each question. Bye.